Good morning, everyone. So, we are getting towards the end of our unit, and we need to just kind of go through and just try to wrap up everything we have talked about because in this particular unit, we have covered so much. So, going to warn you, this video is going to be a little bit longer than normal, and it's just because I want to cover everything all at once. Um, don't feel like you need to take notes per se. Just watch the video because there's a lot of information I'm about to talk through that is review, or you should have seen it prior to this class. Okay, but we're going to try to start trying to wrap up and pull all this different stuff together, and why are we looking at functions and why are they important, and just starting to, again, like I said, pull it together. All right. Okay. So we're looking at key features of functions. Okay. All right. So we are talking about a lot of things in this one. Okay. We're going to talk about domain and range. We're going to talk about x and intercepts and y intercepts, positive and negative intervals, intervals of increasing, decreasing, and constant behavior, parent functions, maxima and minima, and in behavior. And a lot of this is review, so I'll try to also talk fast. Okay, domain. You've done domain and range. The domain is the set of all possible inputs or x values. Okay, to find the domain of a function, we must look at the x-axis of a graph. Okay, also too, if you have a table, it would be all your x values in a table. Okay, all right, so here's some tips on just how to find the domain if you have a graph. You start at the origin and you move along the x-axis until you find the lowest possible x value. This is your lower bound. Then you return to the origin and you move along the x-axis until you find the highest possible value. This is your upper bound. Okay? So you have to be able to say that the domain goes from -2 to 2 on the x-axis. Now your domain may go from negative infinity to infinity. There's no bound on it. Okay. All right, what is the range? The range is the set of all possible outputs or y values. To find the range of a graph, we must look at the y-axis of a graph. Okay. All right, so if I switch over here and I bring up Desmos, oops, did not want to, there we go. All right, and let's say I were to type in, and I like using circles, plus I squared equals 9. Okay. All right. So circles give me a really good chance to talk about your domain and range because circles are bounded. Okay. So when I look right here, okay, and I wonder if I can convert to a table. No, I can't convert to a table because it's not solved for y. Okay. So what I like about circles is that if I'm looking here at the x-axis, so if you can see my cursors right here, okay, when I'm at -3, okay, and I just follow the circle up and around, okay, it stops here at x equals 3. And it's the same thing that's happening at the bottom. So if I start here, so when I go over here and I say, well, I want to say that my domain includes -6. Well, the circle's not over here, okay? This is my function, okay? All right, this is my picture. So that means my domain is restricted to -3 to 3, okay? So I can actually type that in here. It doesn't do anything in Desmos, okay? But my domain, okay, would be from -3 less than or equal to x less than or equal to 3, okay? And don't worry about all this stuff. Desmos just popped up because I'm using Desmos to kind of show you, okay? All right, now the range, same thing. Okay, when I look at the y-axis, okay, and I start here at the origin, okay, the function only exists as long as I'm between 3 and -3. So my range would be the same thing. So my range would be -3 less than or equal to x, no, y, sorry, y, less than or equal to 3, okay? Because that's the only place that that circle exists, okay? Now, if I go back and let's say I use a parabola, so y equals x squared, okay? All right, so my domain. Well, here's where the domain is not, it doesn't end because, okay, if I start here at the origin, okay, and if I move along the graph, okay, you can see my x values. They're just going along. We're at -2 now, okay, and if I zoom out, or zoom, oh, I went the wrong way. So I zoom out, okay, I'm at the origin, okay, my x values just keep going, or my y values, okay, so you're using the x values. So as the x values go to -infinity, okay, those y values, they're just going, okay, and if I were to do the same thing over here, okay, as x goes to positive infinity, those y values, they're just climbing and climbing. They're not ever going to stop, okay? So my domain is all real numbers. There's no bounds on them, okay? But, okay, let me zoom in. Let me go to home, okay? What I start here, okay? So look at my y values. So I'm at 5, I'm at 4, I'm at 3, 2, 1, 0. And then my y values start climbing back up. I'm at 1, I'm at 2. Okay, my y values never get below 0. My y values, or my range, okay, y is greater than or equal to 0. Okay, so there's just some examples of domain and range. Okay. All right, and so there's the steps. Start at the origin, move along the y-axis until you find the lowest possible y value. That's your lowest bound. Return to the origin, move along the y-axis until you find your highest possible value. This is your upper bound, okay? So those are just techniques to help you find domain and range. Okay, intercepts. You should know this as well. X-intercepts is where we cross the x-axis. If you want to find it by hand, you set y equal to 0 in your function and then you solve it, okay? Or you graph it and you just see where it crosses the x-axis like it is here. All right, it has multiple names. X-intercepts also are called roots, they are called zeros, and they're also called solutions, okay? Because like right here, okay, I know that x equals 5, okay? If this was the representation of something that I was trying to solve, okay, it would be at x equals 5. All right, y-intercepts. This is where the graph crosses the y-axis. If you want to find it algebraically, you set x equal to 0 and you solve, and it does not have multiple names. The y-intercept is the y-intercept, okay? All right, positive and negative intervals, okay? So a positive interval says in the diagram, the graph of the function is above the x-axis in the following intervals, okay? So it says -2 to -1. All right, so -2 to -1, okay? This is a positive interval, okay? And then 1 to 2, positive interval. Okay, and it's because the function is above the x-axis. A negative interval says that in the diagram, the graph of the function is below the x-axis in the following intervals, -infinity to 2. So negative infinity is wherever this function, okay, wherever you want to start, okay, up to -2, I'm below the x-axis. All right, -1 to 1. So if I follow -1, and below the x-axis to 1. And then from 2 to, and it should be negative infinity. Let me fix that. Okay. Oh no, it's positive infinity. I'm sorry. I was correct. Okay. I was looking at the y values. Okay. But when you're looking at x values, the x goes towards positive infinity because I'm looking at the x-axis. That was my mistake. Okay. So moving right along. Okay. Now we have types of functions behavior. All right, and this is what's going to be kind of weird. These are just positive and negative intervals. Now we're actually going to be looking at the behavior rather than just looking at the location of the graph as being above the x-axis and below the x-axis. All right, you have what's called increasing behavior. Increasing behavior is when the x value increases, the y value also increases. Okay, and then you might remember someone talking about direct variation. And if you don't, we'll come back to that. Decreasing. When the x value increases, the y value decreases. Inverse variation. And then you have constant. When the x value increases or actually decreases, the y value will stay the same. Okay, so what do I mean by that? So if I go here, it says we use interval notation to represent behavior of a function. The interval measures the x values. The type of behavior describes the y values. Okay, so here's my example. It says increasing. Okay, that is describing the type of behavior of the y values. And then the interval is from 0 to 4. And it's the y values are increasing when the x values are between 0, including 0, that's what the bracket means, and 4, excluding, that's the parentheses. Okay, so you could think of it as having a closed dot and an open dot from 0 to 4. And then the y values, okay, even though the x values are they're going from 0, 1, 2, 3, 4, the y values are actually increasing as well. Okay, so let's look at this diagram. It says the graph is increasing in the intervals negative infinity to negative 1.5. So if I look right here, here's negative infinity on the x-axis. Okay, and so if I start tracing the graph, those y values are getting bigger and bigger and bigger and bigger till right here. Okay, and then if I go over here, start here down at 0, because the x equals 0, and I move to 1.5, I follow my mouse along, my y values are getting bigger and bigger and bigger. Okay, so I'm going uphill, I'm going uphill. Okay, the graph is increasing. Okay, now I'm decreasing when I'm going downhill. So from negative 1.5 right here, negative 1.5 all the way down to downhill. Okay, that is my decreasing interval. And then from 1.5 all the way to infinity. Okay, my y values are getting smaller and smaller and smaller. Okay, all right, parent functions and their graphs. Okay, so parent functions are the basic function that has not been flipped, moved, stretched, or turned. There's all kinds of other different words I could use, but I haven't moved it around. Okay, the parent function also determines the basic shape of the function once a transformation has been applied. Okay, so this is just things that you want to start to recognize in your head. Okay. And your math teachers do this all the time. And some of you might think, well, how do they know that? It's because we've graphed them so many times. Okay. When you've got a horizontal line like this is a constant. So think y equals 2, y equals 5, y equals 6. That's constant. Then you've got linear, you've got absolute value, okay, and you've got quadratic. Okay, you've seen all of these, okay, in work that we've done, okay. Here's square root, here's cubic, here's a cube root, so the cube root of x, Here's a rational function. Here's another rational function. Here's logarithmic. We're going to talk about that. Here's exponential. Okay. You should be familiar with exponential, quadratic, absolute value, linear, especially before coming to this class. All right, then you've got this greatest integer step function, okay? If you were to zoom in on that, that's actually also an example of a piecewise function, okay? But one thing I want you to notice about a lot of your parent functions, not all of them, but notice they interact with the origin, just about all of them, except for your logarithmic and your exponential. Your greatest integer one does. It's right there. Okay. Same thing with your rationals. Okay. So you've only got 4 exceptions, but most of these functions, okay, they originate at that origin, and that's also too what also gives them the name of the parent function. Okay. And this is a good thing. You want to be able to look at an absolute value and be able to determine, okay, how it moved away from the origin. Okay. And that's what we're going to talk about, what you're going to be doing in your Delta math assignment. Okay. So let's talk about how we identify parent functions. So how are your math teachers secretly doing it, like even before they graph it? Okay. Well, one example is special operations. So like when you see absolute value symbols in the problem, okay, that's a dead giveaway that it's going to be shaped like a V. Okay, you can see right here it says, is it a V? Okay, because if it's got any type of V to it, I know it's an absolute value. Okay, when you divide by x, division by x. Okay, so notice here on those rational ones, see how it's 1 over x and 1 over x squared? Okay, and you get these weird looking graphs. Okay, your math teachers are like, oh yeah, once we see that, we know that that's a rational function of some sort. We may not know exactly which one it is, but we've got a pretty good idea. Okay, we're also looking at the highest exponent. Okay, so when you are looking at a problem and it says, hey, I want you to graph y equals x to the third plus x squared plus x minus 2. Well, we know if the highest exponent in that problem was 3, we know that that's a cube function. Okay, a cubic function. So the shape's going to look something like this. Okay. All right, and then when we look at the graphs, we're just asking ourselves, is it a V? Is it a curve? Is it a W? Okay, because when you start getting higher exponent values like x to the fourth, x to the fifth, x to the sixth, seventh, okay, you start getting these shapes that kind of similar. Is it a straight line? A U shape? A U shape, we know that's a parabola, which we know that's a quadratic. Okay, so there's things in the equation and the pictures that give away what type of parent function I might be dealing with. Okay, maximum and minimum points. Okay, so maximum, you might also hear maxima. Okay, these are peaks or hills. Those are the maximum points. So quadratics are great for this. Okay, so this quadratic, it has been flipped over. Okay, and that creates a mountain, which creates a peak, which creates a maximum point. Okay. Then you've got minimum, aka minima. These are valleys, are the minimum points. So if I have a parabola going this way, okay, that's that U shape, okay, you get this lowest point, so you get a minimum, but also a minima. So when is the difference between minimum and minima? So y minima and maxima. All right, the graph shown here, okay, has multiple peaks and valleys that are considered relative when looking at a particular interval. While they may not be the maximum or minimum for the overall function, they are a peak or a valley within the function. Okay. And then you have what's called extrema points. Those are the maximum or the minimum. Okay. It's the highest point or it's the lowest point of the function. All right. So when I go look over here, okay, so you right here, okay, I have a peak, but then I have now a valley. Now I have a higher peak. I have a valley. I have a higher peak. I have a valley, and I have a peak. Okay, so notice I've labeled them. So I've got a relative maxima. This would be a relative maxima, maxima. But the true maximum, okay, would be these 2 points because those are the highest points, okay, for this graph. And you can have more than one because that's exactly where they are the highest, okay? Now you've got all these relative minima, okay? So you've got this minimum or this valley, you've got this valley, and you've got this valley, okay? But this graph has no true minima that I can see here, okay? Because the assumption is that when it's going this way, it would keep going to infinity, negative infinity, just like on this side it would be going towards negative infinity. So since it keeps going, I don't have a lowest point, so I would not say that I have an extrema. Now, if I were to be able to graph every single point, okay, and we determined that it did stop, then I could say, well, my smallest minimum, my extrema is this value. But right now, I can only determine from the graph, okay, that I do have an extrema. I've got 2 of them, okay, because these are the 2 absolute, like they are the maximums of this function, okay? Everything else is just relative. And it's relative because if I'm only looking, if I were to zoom in on this part of the graph right here, you would tell me the maxima is right here, okay? If I were to zoom in on just this portion of the graph, you would tell me that this is the minimum. Okay, so that's all it means by being relative. It's just if I focus on that one spot. Okay, last thing we're looking at is what is called end behavior. Okay, all right, the end behavior of the function is the behavior of the graph as x approaches positive infinity or negative infinity. Okay, it's just what's happening at the very end of the function. Okay, the degree and leading coefficient of a polynomial determine the end behavior. And then the graph shown, it would be noted as x approaches positive infinity, y goes to positive infinity. Okay, so now if I were to be here, okay, the x values would get bigger and bigger and bigger as the y values got bigger and bigger and bigger. Okay, this graph goes off to positive infinity. Okay, and then from the origin going this way, okay, so as I go this way, that graph is going towards negative infinity, okay? All right, so that's my end behavior. So if I were to go back to these parent functions, okay, come on, there we go. Okay, so you can see these parent functions. Look at this quadratic, okay? So as x is going towards positive infinity, the graph goes towards positive infinity. If I start at the origin, as x goes to negative infinity, the graph goes towards positive infinity. So I would say the end behavior on both sides is positive infinity, okay? All right, but if I look at this cube root, okay, in behavior, I'm going off towards, okay, positive infinity, but here I'm going towards negative infinity, okay? And you'll get lots of practices that as we go through the entire semester, okay? All right, so yes, I know this was a long um, video, but I will attach this PowerPoint as a PDF so that way you could just print it off and put it in your notebook as a reference. Okay. All right. I will come back in a second video and talk about what you're going to be doing on Delta Math to kind of work with some of these topics, not all of them.